Okay, well, there are two reactions that are occurring there. One is that the copper 2 carbonate is heated. You know, when you heat something up, you tend to break bonds or cause something to happen. So different things can happen. So for example, you could heat it up and it decomposes into elements. Or you could heat it up and it might decompose into a combination of elements and compounds. Or you heat it up and it can decompose into a combination of compounds, depending on how extreme the temperature is. And so in this particular case, when we heat it up, what can it decompose into? Well, a lot of carbonates, if you heat them up hot enough, they'll give off CO2. And if we give off CO2, what are we left with? We're left with one copper and one oxygen. So that would be copper 2 oxide solid and CO2 gas. So this is a reaction we actually did here. And so this is the first reaction. What type of reaction is this? This is not a redox reaction. This is a Lewis acid-base reaction. It's not a metathesis, and it's not a Bronsted acid-base. I haven't really talked much about Lewis acid-base, but this would be an example. The next reaction here is another example of Lewis acid-base reaction. And that is CO2 gas reacts with lime water. Lime water is a solution of calcium hydroxide aqueous. This is called lime water. Most hydroxides are insoluble, but calcium is soluble. This is another example of a Lewis acid-base reaction, which I'm going to form calcium carbonate plus, okay, what's left over? We take the calcium, the carbon, and 3 oxygens. What's left over? Well, what's left over is 1 oxygen and 2 hydrogens. 1 oxygen and 2 hydrogens, APSO. So what we're going to do is if we pass CO2 through the lime water, we're going to precipitate out calcium carbonate. It's a white, cloudy precipitate in the form. Okay.
There was one more thing.
Okay.
So for the zinc being added to hydrochloric acids, it was again part B, the gas produced by the reaction, A is ignited with the match.
Okay.
Yeah.
All right. Well, when you the first reaction, zinc with hydrochloric acid, there are 2 ways of handling this one. This one, the single replacement works. Zinc is an excellent reducing agent. And then as far as oxidizing agents go, chloride's not a very good oxidizer. So it would be hydrogen ion. Zinc is a much better reducing agent than water. So we can ignore water. This would fit the single replacement form. Or we could do this using the chart method. If we do this using single replacement form, then it forms zinc chloride. In fact, all the single replacement reactions in that lab are all single replacement forms, so you can just go ahead and use that one, which will need 2 HCl's and hydrogen gas. Now, CO2, if you try to ignite the CO2, it doesn't ignite. CO2 doesn't ignite because it's completely oxidized already, but hydrogen will ignite in the presence of oxygen. So we take that hydrogen and mix it with the oxygen in air, ignite it, we get 2 H2O liquids. This is a very exothermic reaction. So what you heard is a little explosion, pop. So we get that energy. And so that would be the second reaction. For experiments 3 and 6, I want you to do the exercise. What was it? Exercise C. Do you know exercise C? Well, there's exercise A, which is the nomenclature. Remember that? There's exercise B, and then there's exercise C. Exercise C is to write the CE, the IE, and the NIE for the various reactions.
So I'd like you to include those as well. I'll give you extra time to do that. It's in at the end of the lab manual, near the very end of the lab manual.
So you'll want this next week then?
Yeah, or later. You can do it. You don't have to have it done for this Thursday. Okay, are there any other questions? No. All right, let's take a look at quantum theory right now.
This is a review. Let's say we're looking at carbon-12 atom, most common atom, carbon-12. We know what the composition of carbon-12 is. What is it? How many protons does carbon have? It's not 12. It would be 6. It's going to be 6. 6 protons plus 6 neutrons gives us a mass number of 12. So let's probably, if you have the periodic table up, let's see. I'm going to put up the periodic table. Six protons and 6 neutrons. The protons and neutrons are going to be in the nucleus of carbon-12. So inside the nucleus, we have 6 protons and 6 neutrons. How many electrons do we have? 6 electrons. Now, where are those 6 electrons? Well, that's what these theories are about. Where are the electrons? Bohr, what did Bohr say where the electrons are? In orbits. Bohr said the electrons are in orbits. So there's an orbit here. That's one electron, and then we have another electron. There's an orbit here, and then maybe another electron. There's an orbit here. How many electrons? We have 6 electrons, so we gotta have 6 orbits, right? Something like that. So we got the nucleus here somewhere, and then the electrons are orbiting around the nucleus, etc. But we know that this picture, is it accurate? Is it correct, this picture? No. The Bohr, this is wrong. The electrons don't orbit. So where are the electrons? Well, in the quantum mechanical model, we say the electrons are in not orbits, but electrons are in shells, or more specifically, within the shells are orbitals. So the electrons are in orbitals. So this would be a representation of the 1s orbital, the sphere. And so we know that this is the wrong picture here, so we need to come up with a new picture of it. And so the lowest energy orbit would be the one that's closest to the nucleus here. But we're dealing with, quantum. Mechanical model. And here, the lowest energy orbital is the, what's it called? The 1s orbital. In carbon has a total of 6 electrons, so 2 will fill the 1s orbital. So if I look at it, let's put the nucleus here. Nucleus. What does 1s orbital look like? Well, there are different ways to visualize what a 1s orbital looks like. One way is just to draw a sphere. But that sphere represents what? Or the circle. If I just draw a circle, what does that circle represent? Or what does the sphere represent? Are orbitals hard shell like this? No. This sphere represents some imaginary boundary, and the imaginary boundary is what?
So is there anywhere the electron could be inside of it?
Yeah. So electrons are going to be inside, so electron might be here, here, here. And so we draw a cloud distribution like this. What does this cloud distribution represent?
95% of them are in and 5% are out.
Yeah, 95% of the dots are in here, 5% are out. Each dot represents the probability of finding the electron there in that position in space. And so what the 1s orbital is going to look like is something like this, where the 95% probability of finding the 1s electron there. Well, we have two 1s electrons, so we'll put one electron here and one electron here. You know, they try to kind of stay apart from each other because they're both negatively charged. And so in one instant, that electron's here, and the next instance up here, 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 and each dot represents a pinpointing the position of that. All right, but we have 6 electrons in carbon, so that takes care of 2. Where do the next electrons go? Yeah, the next electrons go into the 2s orbital, and that can hold a maximum of how many? 2 electrons. And that 2 electrons, max capacity, is dictated by what principle? Pauli something principle. Yeah, that's right. Pauli, does somebody know what it is? Pauli exclusion principle. Right. And so we're only going to get 2. Well, what's the difference between a 1s and a 2s? 2s should be higher in energy. 2s should be bigger or smaller? It's going to be bigger. Of course, a higher energy electron can make it further from the nucleus. And so if we look at the probability cloud for 2s electron, it's going to be spread out farther. I should do this in a different color, but... And so this would be the 2s orbital here. And how many electrons do I have in the 2s orbital? 2. So I can put them here. Let's put it here, here. 2 electrons. One would be spin up. The other is going to be spin down. Like that. That takes care of 4. I have 6 electrons, so there are 2 more electrons. Where do the remaining 2 electrons go? Into the 2p. There are 3 2p orbitals. And, this is what the 2p orbitals look like. This. The difference is just in the orientation. Like, for example, this one's oriented along the x-axis. This one is oriented along the y-axis. So it's just different orientation. It's the same shape, same energy. We have 3 of them. The x, the y, and the z. And so which one should I pick? Should I pick the x, y, or z, or does it matter? It doesn't matter. Actually, I can pick any of the 3 because they're all the same. For my drawing, I'm gonna draw. A p orbital has 2 what we call lobes. One lobe like this, another lobe like that. Those 2 lobes make one orbital. And so the electron can be either in the top one or the bottom one, doesn't matter. So I'll put 1 electron. This p orbital can hold up to 2 electrons. The 2 electrons might both be in the top lobe or both in the bottom, or 1 and 1. And we have 1 electron in that, so I'll put that spin up here. Just say this line corresponds to this orbital with the 2 lobes here. So that's kind of shown here. In the middle, you see that sphere. That's the 2s orbital. And on the z-axis here, there's 1 lobe sticking up and 1 lobe sticking down. That's the p orbital. Okay, the 6th electron, do I pair that in the same orbital, or should I put it in a different orbital?
The same.
Put it in the same orbital? If I put it in the same orbital, like this, do you know that's a violation? Oh, that's a violation of a rule. What rule is that? Hund's rule. That's a violation of Hund's rule. It turns out, if they're the same energy, you know, it's better not to pair it because it's crowded. It's better to put it into the next empty p orbital. Okay, the next empty p orbital, I'm going to squiggle the line. It's not a squiggly boundary, but I'm just going to do this to differentiate the 2 p orbitals without changing the color. Here, I'm going to And so this is another 2p orbital. And that other 2p orbital, I'm going to put one electron in, so let's put it here. So it's better to keep them in separate orbitals rather than pair them in the same orbital, if they're the same energy. You know, if I have to promote this one to a higher energy, then maybe it's not so beneficial to put it into a separate orbital. Maybe it's better to pair it. And so, in other words, we're going to get electron cloud, distribution. That's going to, because the p orbitals are going to have probabilities like this. So let's see what the electron cloud distribution looks like in a carbon atom. This would be a carbon atom here. There's one empty p orbital that's not showing there. And so that's our picture. The picture is very different than orbits. The picture with orbitals looks something like this. You put the electrons in the orbitals. If we fill, this is a filled shell. If I fill the s and the 3 p's, I have a filled shell configuration. The filled shell is a nice, like, spherical symmetry. Do you see it? A nice ball. If it's filled. If it's not filled, it's not going to be so symmetrical. Well, this kind of diagram and this kind of diagram takes up space, a lot of space. What is this diagram called? The y-axis we put E for energy. What's this diagram called? Energy level diagram. We can condense that energy level diagram into this 1s2, 2s2, 2p2. What's that called? A compact, yeah. It's very compact, but we give it a name. What's the name of that? Electron configuration. So this is the energy level diagram. This is the electron configuration. Which one is more informative? Which one tells you more information? Yeah, the energy level diagram tells more information. This one we lose a lot of information. But there's something midway between. It's like halfway between these two. That's what your lab manual calls the atomic orbital diagram. The atomic orbital diagram, we represent each orbital as a box. So we have one s orbital here, followed by a 2s orbital, followed by the 3 2p orbitals. The 3 2p orbitals are going to be 3 connected boxes like that. And then we represent the electrons with arrows. So this would be 1s2, 2s2, and then 2p2. We got 2 unpaired electrons. So this is a bit more informative than the electron configuration, but not as informative as the energy level diagram because we don't space it out. We just draw it next to each other, so we don't see the spacings between the energies of the orbitals. And so that's another compromise there. That's another figure that you might see. The atomic orbital diagram. People get the names mixed up all the time. Electron configuration, atomic orbital diagram, and energy level diagram. They get them mixed up all the time. So, most atoms will want to form bonds. They'll want to bond to other atoms. Atoms that don't want to bond are the noble gases. The reason why atoms want to bond is to increase stability. So, for example, one thing that carbon can do is it's got these empty orbitals. In fact, if it gains, let's see, 4 more electrons, it would have a filled shell. If it loses 4 electrons, it would have a filled shell, filled 1s shell. And so that happens because of chemical bonding. So let's talk about chemical bonding next. There are three major types of bonds that we're going to look at.
this chapter. There's the ionic bond. The ionic bond holds ions together in an ionic compound. There's the covalent bond. The covalent bond holds atoms together in the molecule. And then there's the metallic bond. The metallic bond holds metal atoms together in a metal. But all the bonds rely on electrical attractions. Whether it's ionic, covalent, or metallic, we're relying on positive being attracted to negative. Let's look at ionic bonds first. We have cations, which are the positive ions, and anions, which are the negative ions, cations and anions. Let's take a look at nitrogen. Nitrogen has 7 valence electrons, no, not 7, it has 7 electrons, but not all of those are valent. If I look at the 7 electrons on nitrogen, 2 of them are core, 5 of them are valence. And so nitrogen has 5 valence electrons. The 5 valence electrons we represent as dots there. So to fill up its valence shell, it just needs 3 more electrons. We want 2p6. And so if nitrogen gains 3 electrons, we can fill up its valence shell, and we'll have the ion nitride. So nitrogen there with 5 dots, nitride with 8 dots. Those 8 dots represent the filled valence shell, that is the 2s2, 2p6. And the total of 8 valence electrons is what we call an octet. This is the Lewis symbol for nitride. This is the chemical formula for nitride. The Lewis symbol formula. When we fill up the octet, then if we fill up the first shell, that's like helium. If we fill up the second shell, that's like neon. Neon has 10 electrons. So we got 10 electrons here. Oxygen has a total of 8 electrons. 2 of those are core for the helium, and that leaves us with 6 in the valence. We don't differentiate between the S and the P. We just count them all together. So 6 total. There's 6 total. That's 6 dots around here. That's 2, 4, 5, 6. In order to fill the second shell, we need 2 more electrons, so oxygen is a good oxidizer. Is nitrogen a good oxidizer? Turns out nitrogen is not a good oxidizer, but oxygen is. And if oxygen takes 2 electrons, we'll form oxide. Oxygen can oxidize many things. Nitrogen can oxidize a few, and so it's possible to form nitrides. Anyway, oxide is going to have 10 total electrons. What's important here is that it's got the octet, and it's 8 valence electrons here. The 10 total electrons, it's got a filled shell like neon. Fluorine is just 1 electron short. It's got a total of 7 valence electrons, shown as 7 dots here, 3 pairs and 1 single. If fluorine gains 1 electron, it'll have a total of 10 electrons, 2 core electrons and 8 valence electrons. The 8 valence electrons is an octet, which is a filled shell configuration. So it's like neon. Neon's down here. Neon has 10 electrons. Neon's already got an octet. It's got a filled first shell, filled second shell. Does it want to gain or lose? It doesn't want to gain or lose. It's already got the full shell. And so neon's very unreactive. It's got that octet. 10 electrons.
sodium, sodium is a filled first shell, a filled second shell, and a partially filled third shell. The third shell is only one electron, 3s1. For sodium, it's much easier, to get rid of this one valence electron. Sodium has a relatively low ionization energy, pretty good reducing agent. You get rid of that electron. I'm giving it to some oxidizer. And so if it loses that valence electron, then we're left with 1s2, 2s2, 2p6. 1s2, 2s2, 2p6 is the same as neon, 10 electrons. This is sodium ion. Magnesium with 2 valence electrons. We lose those 2 valence electrons, we end up with a filled shell configuration of neon, 10 electrons. Aluminum has 3 valence electrons. We could lose all 3 of those. Come up with aluminum 3+ ion, which is filled shell, just like neon with 10 electrons. And so here are the charges. So the species on the right, it's easier to fill up the valence shell with electrons. The species on the left, it's easier to lose the electrons. The species in the middle, like in this region here, can go either way. Take electrons or they can lose electrons. In fact, all these can take electrons, lose electrons. This one is more preferred than the other. Write the electron configuration for calcium ion. So we could do that based on the periodic table. So let's go to the periodic table. All right, calcium is here. So if we look, the first shell is filled, the second shell is filled, the third shell is filled. When the third shell is filled, we're at argon. And so we could start this by just using argon to represent the first through third shells being filled. And once we're past argon, then we're in what orbital here? First, second, third, 4. We're in 4s1, 4s2. 4s2. So this is calcium. Calcium has how many valence electrons? 2. Yeah, I can represent those as 2 dots. Now, if calcium loses those to some oxidizer, then we're going to be left with just the core, that is the argon filled shell configuration. The 4s2 electrons are now gone. Argon, again, is the first shell is filled, the second shell is filled. So 1s2, 2s2, 2p6, and the third shell is filled, 3s2, 3p6. So the first through third shells are filled. Take a look at their electron configuration for calcium. Does it look a little weird? Look at that slide and look at the electron configuration for calcium. 1s2, 2s2, 2p6, 3p6, 4s2. Yeah, it's missing the 3s. So there's an error in that electron configuration is wrong. How about for calcium 2+? For calcium 2+, this is correct. They have the 3s in there. So first shell's filled, second shell's filled, third shell's filled. So this is like argon. So it'd be isoelectronic. Isoelectronic just means the same number of electrons. So it's isoelectronic with argon. Has the same kind of electron configuration. All right, let's take a look at ionic bonds first. Ionic bonds are the bonds that hold ions together. So let's let's actually look at the formation of sodium chloride. This is making sodium chloride by using sodium metal and reacting with chlorine gas. So here's a video on that reaction. Let me show you what they have here. On this cutting board here, they have some sodium metal. In this Erlenmeyer flask, this is a chlorine gas generator. Do you know how they make chlorine gas? To make small quantities of chlorine gas, you take potassium permanganate. Potassium permanganate is purple stuff. So you take some potassium permanganate and you mix it with hydrochloric acid. So potassium permanganate. What can you tell me about potassium permanganate? When you think of potassium permanganate, does anything stand out with potassium permanganate? Yeah, the formula is KMNO4. So what do you know about KMNO4? What's that? Hmm? There's no chlorine in it. Tell me one chemical property of potassium permanganate that stands out. Maybe nothing. There's no chemical properties that stand out.
Would it be an oxidizer?
Would it be an oxidizer? Yes. It is an oxidizer. How could you tell it's an oxidizer?
4 oxygens.
4 oxygens.
An oxygen is a powerful oxidizer.
Oxygen's a powerful oxidizer. Well, not these oxygens. These oxygens are not powerful oxidizers.
The manganese is electron poor.
The manganese is electron poor. Good. How poor is it?
Five.
Not +5.
What's that?
+7. Good. Do you remember we were talking about this the other day? Yesterday? You know, scandium is +2, right? +3. Pretty much +3. Titanium, +2, +3, +4. Chromium, 2. +2, +3,
Plus 4, 5, 6.
4, 5, 6. 6 is the max, right? Actually, chromium 6. Movies have been made from chromium 6. Do you know what movie chromium 6 was a star in? It's a movie called Aaron Brockovich. Apparently, chromium 6 was contaminating some well in the San Joaquin Valley of California. A lot of people were getting sick. So that's chromium 6. Well, chromium 6 says, yeah, this is going to cause some problems if you're consuming chromium 6, because chromium 6 should be a powerful oxidant. Manganese?
Plus 7.
+2, +3, +7. Yeah, +7, that's a lot of electrons to lose. I mean, if you think about manganese, that's a heck of a lot of electrons to lose. But what is manganese? Manganese is going to have the filled argon core to a point. And then after argon, what's the next orbital? 3s. No, not 3s. 3s. 4s. Actually, maybe I should do. It goes argon to the next orbital will be 4s. 4s. How many?
2.
2. And then 3d. 3d. How many? Well, we'll just count them. 3D1, 3D2, 3D3, 3D4, 3D5. So in order to get manganese plus 7, you would have to lose all the S. Which one goes first, the S or the D? The S. You'd have to lose all the S first, and then you would have to lose all the D, which are considered inner shell electrons. You'd lose all the Ds. And then we have manganese 7. You think that's going to be an easy thing to do? Lose 7 electrons? No. So this is why. Permanganate is a standout because of its very high oxidation speed. So you're right, it's going to be an oxidizer. That's good. So what types of things can permanganate oxidize? Lots, right? Permanganate can oxidize lots of things. You got to be careful. Screw this up. Wait, this. I don't know what's going on. Why the bottles are labeled like they're labeled here. But anyway, what we got here is we have a potassium permanganate in here, and then add some hydrochloric acid. If we add a hydrochloric acid, what's the potassium permanganate going to oxidize? This is the aqueous potassium. It's not going to oxidize water because there's already water present here. This is the aqueous potassium permanganate. It shouldn't oxidize water because we've got aqueous potassium permanganate. It's got to be stable with water. And so it's got to oxidize something with hydrochloric acid. What will it oxidize? The what? Chloride. It's going to oxidize the chloride. Is chloride a good reducing agent? Is chloride a good reducing agent? Well, let's take a look at the redox chart. This is some redox chart. It's just random redox chart I just grabbed off the internet. So, is it going to oxidize? Well, is chloride a good reducing agent? No, it's a bad reducing agent. But permanganate is a great oxidizing agent, so maybe it'll work. And in fact, permanganate is a great oxidizing agent. On this chart, it's number 4. On our chart, it's like number 5. What's the best oxidizing agent? On this chart, it's fluorine. On our chart, it's the best oxidizing agent. Best reducing agent is lithium. Best oxidizing agent is, on our chart, the thing to do is to review this stuff periodically. You see, like our chart, fluorine, but the best oxidizer on our chart and the best oxidizer on this chart is fluorine. Number 2 is different though. Number 2 on this chart is cobalt 3+. Number 2 on our chart is, so it's different. But anyway, permanganate's a powerful oxidizer. Permanganate is capable of oxidizing what? It's capable of oxidizing chloride. Permanganate is capable of oxidizing any reducing agent stronger than what? Is permanganate capable of oxidizing bromide? Is permanganate capable of oxidizing silver metal? Yes or no?
Yeah.
Yeah. So do you guys remember how to use the chart? Okay, good. So anyway, permanganate is capable of oxidizing. It's not capable of oxidizing gold, chloride, chromium-3. In fact, permanganate can convert chromium-3 to chromium-6. It's capable of oxidizing water, but if permanganate is capable of oxidizing water, why can we make aqueous potassium permanganate? Well, it's because this is an exception here. There's going to be chloride, water, and hydrogen ions present. And so, what's easier to oxidize, chloride or water? According to this chart, what should be easier to oxidize, chloride or water? Water. But it turns out it's more difficult to oxidize because this chart deals with energy. And so if we oxidize water, we'll get more stability in return. But what we don't see is that it's a heck of a lot easier to oxidize chloride. To oxidize chloride, all you have to do is pluck an electron out of the outermost orbital. Here. To oxidize water, you have to rearrange everything. The bonds have to be broken and whatnot. So it's actually more complicated to oxidize water than chloride. And so even though the return isn't as good, it doesn't form something quite as stable, it happens a lot easier. And so the path of least resistance is taken, so chloride becomes oxidized, water is left alone. Even though if we were to oxidize water, it forms something more stable than chlorine. And so that's just one exception on the chart. This one, we're going to go against what the chart says, and we're going to oxidize chloride. So permanganate oxidizes the chloride to form chlorine. So we're going from a stronger oxidizer to a weaker oxidizer. And so that's the whole concept behind the chlorine generator. What do I do with it? Oh, there it is. Okay, so you mix the potassium permanganate with hydrochloric acid, it'll start generating chlorine gas. Fast forward this a little bit. So they're cutting some sodium metal there. The sand here is just as a heat sink, so the glass doesn't get too hot. All right, so they put in the hydrochloric acid. This person didn't label the bottles correctly. You pour in the hydrochloric acid, then they're going to cap it. They cap it with a one-hole stopper. And this is the gas that's generated here is going to go out this tube and then end up inside the flask here. This person's going to add some more hydrochloric acid. I'm pretty sure that's hydrochloric. That wouldn't be zinc chloride. It could be zinc nitrate. Makes no sense. It should be hydrochloric acid and potassium permanganate. You know, most redox reactions are quite violent. They except chloride's such a poor reducer, he doesn't have to worry about an explosion. Permanganates, you do have to worry about explosion, but chloride's very hard to oxidize. This person's going to put in some more potassium permanganate crystals, I think. They're putting in there. Yeah. Now the reaction's starting to go. But you have to be very careful with redox because the potential for explosions is high. So generating this green gas, green-yellow gas, and it's starting to fill up the flask here. It's not a huge amount of gas that they're, generating here. And so you can see the chlorine gas in there now. Let me fast forward then. Okay, now taking a piece of sodium. Sodium is a very soft metal. I'm going to place that in. This is being done in the hood, by the way. So, this is a potentially violent reaction because sodium is a powerful reducer, chlorine is a powerful oxidizer. So if you have a powerful reducer and a powerful oxidizer combined, it's explosive. But you look at this, nothing seems to be happening, right? It looks like a very slow reaction. But these types of reactions are very deceptive because they happen exponentially. Like in one instant, nothing's happening, and in the next instant, you have an explosion. And it has to do with temperature. Usually if we have a solid like this, the reaction's kind of slow. So what this person is doing is adding a little bit of water there to heat things up. You see a little drop of water. And so the sodium is getting hot. Now, once the sodium gets hot enough, then it will react quite quickly. But if you just let it sit there, eventually it would explode like that. And so the sodium reacts with the chlorine and forms sodium chloride. This vapor here is just sodium chloride crystals. Vapor of sodium chloride crystals. Fog. So let's take a look at the reaction between sodium and chlorine in more detail here. So I'll do it on the board. If we look at sodium, how many valence electrons does sodium have? One valence electron. What is the electron configuration for sodium? Neon. 3s1. Neon 3s1. And then what we're going to do is we're going to react it with chlorine. But what I'm going to do is chlorine is diatomic. I'm going to split it into atomic chlorine. The diatomic chlorine looks like this, the Lewis structure. So what we'll do is we'll split it apart into a chlorine atom. So we have a chlorine atom. Chlorine has how many valence electrons? Chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. And what's the electron configuration for chlorine? Neon.
S2.
Yeah, 3s2.
3s2, yeah, sorry.
3p.
And then 3p, 1, 2, 3, 4, 5.
3p5. Now chlorine's a powerful oxidizer, and what's going to happen here is it's going to try to take electrons. Well, sodium, sodium's kind of a big atom. Big atoms are not so hard to ionize. Look at sodium atoms. In fact, the metals, the alkali metals, are all kind of big. Plus they have that one valence electron. So if we look at the alkali metals are the easiest to oxidize, are the biggest, and then the alkaline arcs are pretty easy. Then it gets harder to go across. But sodium's fairly big, it's not so hard to ionize. It has a relatively low ionization or a relatively high ionization. If something's easy to ionize, does it have a low ionization energy or a high ionization energy? Low. And so what's going to happen here is chlorine wants another electron, and then it's going to fill its third shell. And so it's going to strip that electron off sodium. when it strips the electron off sodium, let's first draw the Lewis structure for this. Then sodium's going to lose that one single valence electron, so it's going to lose that, and that's going to create a charge, imbalance of charge. That imbalance of charge is a result of having now 11 protons and 10 electrons. So here's the sodium atom and chlorine. Actually, which one is bigger, sodium or chlorine? Sodium is bigger. Let's take a look again at the previous slide here. Why is that? Here's sodium, here's chlorine. Notice, they're both in the same shell. Sodium is bigger than chlorine. Why is that?
Because the more amount of circles,
The more amount of circles?
so
The more of what? It's not the circle, it's more of
the more energy it takes to take.
more energy. I would say chlorine is smaller. Chlorine is smaller because,
More electrons.
More protons.
no, more protons. The electrons are in the same shell, so electrons try to stay away from each other. But if the number of protons increases, then these individual electrons are going to see that. And so chlorine is smaller because it has more protons. Electrons are in the same shell. And so we could draw it like this. Here's the sodium atom. Here's the chlorine atom. Sodium atom has 11 protons and 11 electrons. Chlorine atom has 17 protons and 17 electrons. 17 protons, 17 electrons. Okay, so if sodium loses one electron, then its electron configuration is just going to go to neon. So we've lost that valence electron here. And so what results here is a sodium ion. The sodium ion has 11 protons and 10 electrons. So we'd say it's isoelectronic with neon. This is a 10 electrons. Well, what happens is this. What happens is now we got 11 positive charges and only 10 negative charges. If that happens, the 11 positive charges pull in the electrons closer. And so the sodium ion is going to be about half the size. And so the size is going to shrink down to about half the size of the sodium ion. And so cations are about half the size of their parent element. Now chlorine is going to gain that electron. So now chlorine is going to have a filled shell or an octet of electrons here. And chlorine is going to be isoelectronic with argon. Because if we gain one more electron, we fill the first shell, second shell, that's neon, and the third shell. If we fill the third shell, then it's isoelectronic with argon. But the size changes dramatically. In fact, when we create an anion, anions are about twice as big as the element. And that's because we have 17 protons, but now we have 18 electrons. 18 electrons is like argon. 18 electrons with 17 protons. The 17 protons have a hard time pulling in all 18 electrons. And the slide gets inverted. Okay, this is what we call a Lewis structure. Here. That's a Lewis structure. And what is an ionic bond? The ionic bond is just, it's not shown, but ionic bond is just having the positive cation and the negative anion adjacent to one another. So that's called the ionic bond, let's put it. So this would be the ionic bond here. Positive, cation, negative. But we just don't form one ionic bond. This would be a Lewis structure for a formula unit. In ionic bonding, we form many, many bonds. We form a lattice like this. And in the lattice, we have positive and negative balls. So if we have a positive, then we want as many negatives to be in contact with it, because positive and negative is favorable. And if we have a negative, then we want as many positives to be in contact with it. And so what we build up is a lattice type structure. A lattice type structure is going to have many, many formula units incorporated into it in 3 dimensions. And so we'll have the salt lattice there. Check something here. Plug this in. Okay. And so here we can see the lattice. Blow up the lattice here. So in ionic compounds, we don't form molecules, we form lattices. Like this. And the ionic bond, we have lots and lots of ionic bonds here because an ionic bond is just having a positive next to a negative. And so right here, if I look at this positive, how many ionic bonds do I have? I have 1, 2, 3, 4 ionic bonds, just shown there. If I built this up into 3D rather than 2D, I'd have 6 ionic bonds to each ion, not just 1. It looks like there's only 1, but it's not the case. We can see it here. This is the expanded lattice here. This is it. So if we pick one of these center ones, like this gray one inside here, we count 1, 2, 3, 4, 5, 6. And then if we look at a green one, we count how many gray ones. 1, 2, 3, 4, 5, 6. So 6 direct ionic bonds there. But ionic bonds are just an attraction between positive and negative, and so they're secondary ionic bonds, tertiary ionic bonds as well. Ionic bonds are strong. Like, for example, sodium chloride. Sodium chloride, is it easy to melt this stuff? Have you ever tried to melt salt on the stove? No, it's hard to melt. That's because the ionic bonds are strong. This lattice is strong. Does sodium chloride conduct electricity? It doesn't. It doesn't conduct electricity because there's no translational mobility of the ions. The ions are stuck in position. However, if you could melt it, and you can, if you did melt sodium chloride, then it would conduct electricity. This is a molten salt here. And molten salts conduct electricity because now you broke apart the ions and now they can move around. And those moving ions can conduct electricity like this. Another way you could break apart the ions is by dissolving it in water. Sodium chloride is highly soluble, and so it's hard to melt the stuff, but it's easy to dissolve it and break apart the ions that way. And so aqueous sodium chloride is a good conductor of electricity, or salt water is a great conductor of electricity. But the solid is not. Okay, that's some ionic bonds. Okay, let's take a break here and then we'll do one more example of ionic bonds.